Hello, welcome to this lecture. In the last lecture, we have seen the definition of tangent vectors and tangent space of a regular surface. In this lecture, we'll give some examples of tangent space. So let us begin. So let us first recall the definition of tangent vectors. So suppose you take a regular surface in R3. So let S be a regular surface in R3. And let us take a point P in S. So suppose this is my surface S, and this is the point P. Okay. So in order to define tangent vector, so what I have done, so I have taken all those differentiable curves passing through the point P and take the velocity vector of that curve at this point. So suppose this is my alpha, and alpha is defined on a open interval minus epsilon to epsilon, such that alpha of 0 is equal to p, and this will be my alpha prime 0. So this tangent vector is alpha prime 0. So let alpha be a differentiable curve on S such that alpha 0 is equal to p. So alpha prime 0 is a tangent vector at P. Okay, so the tangent space of S at the point P, it is the collection of all this alpha prime 0 such that, so this alpha is a differential curve on the surface S passing through P. Okay, so this is my definition of tangent space, and so this tangent space, so it is a vector space of dimension 2. So TPS is a vector space of dimension 2. Okay, and correspondingly, so I'll get a tangent plane. So I'll get this tangent plane here. Yeah. So this is the tangent plane at P. Okay, so notice only one thing. So this plane, it is a plane in R3. So this, if P is not equal to origin, so this is not a vector space. But if I shift this tangent plane to origin, so then it will be a vector subspace of R3 of dimension 2. So nevertheless, I mean, if I take these vectors, so this alpha prime 0, so these are my vectors, okay? So, and if I take this point to be x, y, z, and this alpha prime 0, okay? So this will correspond to x, y, z minus p, okay? So in that sense, so this tangent plane also you can think as a vector space. Okay, so rigorously it means that if I transfer this or translate this tangent plane to origin, So then it will be a vector space of dimension 2. Okay, so now we'll be interested to find tangent plane at the point P. Okay, so now let us take a regular surface in this way. So let us take, so let f R3 to R be a differentiable. Also let us take smooth function, differentiable smooth function, such that, so 0 is a regular value of f. Okay, so if 0 is a regular value of f, so this will imply that f inverse of 0, so this is nothing but, as I said, it is all those point x, y, z belongs to R3, such that fxy z equals to 0 is a regular surface. Okay, so this will be a regular surface. And now let us take, so let S belongs to f inverse 0, and let us take a point and let P equal to x naught, y naught, z naught belongs to S. Okay, so we'll be finding the equation of tangent plane at the point P to the surface S. Okay, so how we are going to do that thing? So because this x0, y0, z0, it belongs to S, so this implies that f of x naught, y naught, z naught, it is equal to 0. Okay, so now from the definition of tangent vector, so how to get a tangent vector? So let us take a, so alpha minus epsilon to S be a differentiable curve in S such that so f such that uh, alpha of 0 is equal to x naught, y naught, z naught. Okay, all right, and because this alpha it lies in S, and also we have, so f of alpha t is equal to 0. Okay, so f of alpha t, it is equal to 0, and okay, so now so if I take the differential of f, so then what I'll get is the following. So this f, it is a map from this R3 to R. So let us take the differential of this f at the point x naught, y naught, z naught. So it again, it will be a linear map from R3 to R. Okay, and so so this at the point alpha prime 0. Okay, so this will be equal to what? So first you take the this Jacobian matrix corresponding to this f. So it will be partial derivative of x f at the point. So del f del x at the point x naught y naught z naught. So del f del y at the point x naught y naught z naught. Maybe I'll write it here. So differential of this map, so evaluated at the point alpha prime 0. So this is, so del f del x at the point x naught y naught z naught, del f del y at the point x naught y naught z naught, del f del z at the point x naught y naught z naught, multiplied by this vector. Okay, so again let us take, so let alpha t equal to xt, yt, zt. Okay, so alpha prime 0, so this will be x prime 0, y prime 0, z prime 0. Okay, so this will be equal to x prime 0. So del f del x evaluated at the point x naught y naught z naught plus y prime 0 del f del y x naught y naught z naught plus z prime 0 del f del z x naught y naught z naught. Okay, so now so this f of alpha t is equal to 0. So this will imply that, so this df x naught y naught z naught evaluated at the point alpha prime 0. So this is also equal to 0. So therefore from these two equations, equation 1 and 2, so what we'll get? So from 1 and 2, so what we'll get is the following. So del f del x at the point x naught y naught z naught multiplied by this x prime 0 plus del f del y evaluated at the point x naught y naught z naught multiplied by y prime 0 plus del f del z at the point x naught y naught z naught multiplied by z prime 0 is equal to 0. Okay, all right. So this shows that, so if I take the grad of f at the point x naught y naught z naught and take the dot product with this x prime 0, y prime 0, z prime 0, so this is equal to 0. So that is, this grad of f at the point x naught y naught is perpendicular to this tangent vector. Okay, so this grad is perpendicular to or orthogonal to this tangent vector alpha prime 0. Okay, so now let me again draw this picture. So suppose you have the surface S. So and the surface is given as xy z such that f of xyz is equal to 0. And now you have taken a point P here, and suppose this is my tangent vector alpha prime 0, and this grad, it will be orthogonal to this tangent vector. And here this alpha is just an arbitrary tangent vector. So therefore, so this grad, it is orthogonal to this tangent plane. So this is orthogonal to this tangent plane. Okay, so let me write down. Is orthogonal to tangent plane P at the point x0, y0, z0. Okay. All right. So, okay. So now, so what will be the equation of this tangent plane now? So now let us take any point. So x, y, z in this tangent plane. So x, y, z, it belongs to the tangent plane. So this implies that, so if I take this vector x minus x naught, y minus y naught, z minus z naught, if I take this vector, so this will be orthogonal to this grad of f at the point x naught, y naught, z naught. Okay, so therefore this dot product will be equal to 0. So from here, I'll get the equation of the tangent plane. So the equation of the tangent plane is the following. So x minus x naught multiplied by del f del x at the point x naught, y naught, z naught plus y minus y naught del f del y del f del y at the point x naught, y naught, z naught plus z minus z naught times del f del z x naught, y naught, z naught. So this is equal to 0. Okay, so this is the equation of the tangent plane at the point x naught, y naught, z naught. Okay, so the speed is the tangent plane, and so this, if I take this space, so let w is equal to p x naught, y naught, z naught minus this vector. Okay, so this implies that, so this origin, it belongs to this w. Okay, so I have just translated this plane to the origin, and so this w is a vector subspace of R3, and dimension of W is equal to 2. Okay, so this, so therefore, so this implies that, so W is the tangent space of S. Okay, so is a tangent space of S. Okay, so corresponding or maybe I'll just change this. So W is the tangent space of S corresponding to the point x naught, y naught, z naught. Okay, got it. So for instance, if I take this map, so example, so let us take, so let fxy z is equal to x square by a square plus y square by b square plus z square by c square minus 1. So you can check that. So this 0 is a regular value of this f. So 0 is a regular value of f. Okay. So then, so f inverse 0 is a regular surface. Okay, and what is f inverse 0? So this implies that, so this S so this is a regular surface. Okay, and now let us take a point. So let x naught, y naught, z naught, it belongs to S. Okay, so the tangent plane at x naught, y naught, z naught of S is given by the equation. So x minus x naught, and so del f del x evaluated at the point x naught, y naught, z naught. So what will be that? So this will be twice x naught by a square plus y minus y naught. So del f del y evaluated at the point x naught, y naught, z naught. So this will be twice y naught by b square plus z minus z naught multiplied by twice z naught by c square is equal to 0. So this is equal to 0. So therefore, so what will be the equation of this tangent plane? So it will be x minus x naught by a square plus y minus, sorry, x multiplied by x naught by a square, y multiplied by y naught by b square plus z multiplied by z naught by c square minus x naught square by a square plus y naught square by b square plus z naught square by c square equal to 0. So therefore the equation of this tangent plane is x naught by a square plus y naught by b square plus z naught by c square equal to 1, because so this x naught, y naught, z naught, it belongs to S. So therefore, so this equation, so this summation will be equal to your 1. So this is the equation of tangent plane. So this is the equation of tangent plane. Okay, so I'll stop here. So we'll continue. in the next class.